too bright. So I remember seeing this in the homework problem and thinking it was hard to do. So let's look at the following problem. We want to, welcome, thank you. We want to find the volume of a parallel pipette. Again, you hear parallel pipette, you're just thinking like a three-dimensional rectangle or a rectangular prism or a parallelogramal prism. I don't know how to, like something that's not like super weirdly shaped. If we are given all 8 vertices. So here they are in no particular order. A is the vertex 8, 20, 0. B is the vertex. I should get this so I can see it better. 2, yeah. Oh, thank you. I was like, what do you mean eraser? Yes, exactly. An old school pink eraser is a good example. The ones that were kind of like slanty. That's a good example of like a parallelogram, parallel pipette. Thank you. I was like, that makes sense. -6. C is 11, 23, -4. D is -1, 7, 3. E is -1, 13, -2. F is 2, 22, -11. G is 11, 29, -9. And finally, H is 8, 14, 5. So the thing about this is, welcome, we're told it's a parallel pipette. So there should be some vectors that are parallel to it, because the idea here is we essentially want to find, right? We want to find, so if we're thinking about the parallel pipette looking vaguely, you know, like this, we whoops, that, sure, like that. Our job is to find the vectors u, v, and w that all emanate from the same vector, or sorry, vertex, so that we can find the volume as being the magnitude of u cross v, sorry, the absolute value, not the magnitude, of u cross v dotted with w. That's what we need to do. So we need to kind of figure out which vectors are parallel and eliminate those essentially. So this problem really is just a, let's look for some parallel vectors. And you kind of have to do some guessing and checking. There's not really, I've done this problem with students before. I'm like, there really isn't a good way of just being like, I can totally see which ones are which. We really just have to test something. So I'm going to look at for E minus A, or sorry, A minus E. So the vector EA, I'm going to do these ones minus these ones. So EA, no, sorry, A minus E, apologies. 8 minus -1, and then 20 minus 13, and then 0 minus -2. So there's EA. Okay, let's look at DH. So let's see, I have, again, it's the end minus the beginning. So 8 minus -1, 14 minus 7, 5 minus 3. Well, that's good. Thank you. So I've got 2 vectors that are parallel already. Let's look at, so, I mean, I'm quote unquote guessing, but I did this problem ahead of time. So I kind of know, I don't want to like waste our time guessing things that aren't good guesses. So we're doing this with some prior knowledge. HA, so I'm ending at A, I'm starting at H. So 8 minus 8 is 0. And then 20 minus 14 is 6. And then 0 minus 5 is -5. Then I want to look for something that is also going to get me that. So let's see. Do I see any other ones that have the same first 2 components? I see D and E. That looks plausible. So if let's see, I want to end at E and start at D. So -1 minus 1 is 0I. And then 13 minus 7 is 6J. And then -2 minus 3 is -5K. K. Sorry, I've been, oh man, you guys let me get away with murder over here. Sorry, that should be 9i plus 7j plus 2k. Should be 9i plus 7j plus 2k. Should be 0i plus 6j minus 5k. This should be 0i plus 6j minus 5k. Cool. Yeah. Good with the I. Yeah. So ijk, 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 ijk. Sounds like I'm joking. ijk. Welcome. Thank you. So we can see that these two vectors are parallel, as are these, because they go in the same direction. For those of you just walking in, we're talking about how to find the volume of a parallel pipette given all 8 vertices. And it's kind of a big pain in the butt. So what we've got so far is kind of essentially the base of our parallel pipette. We can see that if we look at EA, so let's say this is EA and DH, those are parallel. And then DE and HA are also parallel. Cool. So now the other 4 points, they're going to form the top somehow or the side, right? Like you might think of this as the side or the bottom. I don't know. It's kind of hard to tell without actually drawing it out. So let's see, looking at these same points, let's go this way. So let's see, let's look at, say, I don't know, BF maybe. So you can see this problem is time consuming, right? Like you have to just try a bunch of stuff. So let's see, BF is 2 minus 2. I'm gonna do it the right way this time. 22 minus 16, so 6j. Negative 11 minus 6 is minus 5k. Well, that's looking promising because that's exactly the same vector I ended with before. So I can see that this BF, even though it doesn't have any of the same points as HA or DE, it's going to essentially go in the same direction. So it's going to be kind of like above this. And then I would love to find another vector. Let's see, I've already used A, E, D, and H. I just used B and F. I bet C and G is probably where I'm looking next. So let's see, if I do G minus C, so start at C and end at G, I'm going to get 11 minus 11, 29 minus 23, negative 9 minus negative 4 is minus 5. Okay. Also, yeah, for those of you just coming in, let me give you the attendance link again. For those of you that just came in, the attendance things are there, fill them out at some point. And then let's see, we probably need to do something with BC and FG. So let's look at, so I'm trying to get something that's parallel to this. So I'd like a 9 to come up. So let's see, looking at BG and BC, if I do this one minus that one, I get 11 minus 2 and 29 minus 16. I don't think I want a 13 in the, oh, you can't see I'm looking, sorry. If I do 29 minus 16, I'm gonna get 13, and I don't want a 13 in the second component. So I probably want to do these two together, because 11 minus 2 is 9, and 23 minus 16 is 7, and negative 4 minus negative 6 is positive 2. So we're really trying to look for parallel vectors here. So I'm going to have BC, and that's going to be 11 minus 2, 23 minus 16, and negative 4 minus 6. And then in a similar way, if I'm doing BC, I'm probably also doing FG. Yeah. So we get, all right, 11 minus 2 is 9i, 29 minus 22 is 7j, wow. And negative 9 minus negative 11 is plus 2k. So essentially, what I've got so far is I've got the bottom here, which is like my E, A, D, H, and then above it, parallel to it essentially, is my sum. Now I don't know if I've really drawn these in the right order, but I've got my B, C, and my F, G, like that. Or maybe they're flipped over, like I don't actually know. So now I'm going to try and get from the bottom to the top. And again, here are my points. So can I just go from E to B? Is that going to work? And from D to F? if that was going to work, those would have to be the same. Let's see if that works. So from E to B, so EB is going to be, let's see, 2 minus 1 is 3I, 16 minus 13 is 3J, and -6 minus -2 is -4. Okay. And then does DF give me the same sort of thing? Let's see, DF. So let's see, I'm going to have 2 minus -1, that's a 3I. I'm going to have 22 minus, no, that doesn't work out so well. So those aren't parallel. So maybe the way I've drawn this, maybe I've really got things kind of backwards. So that's not looking so good. Let's try something else. Let's try EF. Maybe I've really misabled these. So EF is looking like, let's see. So from E to F, I'm going to get 3I, and then 22 minus 13 is 9J. And -11 minus -2 is -9K. Wow, this is a pain in the butt. Really enjoying this problem so much. It's a fine problem. And then let's try DB, because maybe really I mislabeled these and these should be turned around like that. And so then if I do DB, let's see what I get. I get D minus B, so -1, sorry, B minus D, wow. So when you're doing the vector, right, it's always the end one minus the beginning one. So 2 minus -1, 16 minus 7, looking good. -6 minus 3, yeah, right on. And then in a similar way, we probably want AG. And we probably want HC. So if we do that, let's see, DB is DB, ending at B, starting at D. So 2, oh, sorry, I just did DB, apologies, AG. So ending at G. So 11 minus 8, and then 29 minus 20, and then -9 minus 0. Oh, look, it's even the same, right? So, and that makes sense, right? If this is like the top and this is the bottom, then all 4 of those vectors getting you from the bottom to the top should be like the same vector, because it should be the same distance. And then finally, we don't really need HC here, but we should see that it is in fact the same. Okay, so now we can kind of draw our picture. And I've drawn it a little bit wrong, if that's okay. But really it looks kind of like this. So it does look like E, A, D, H. But then above E, we actually want F. And above D, we actually want B. And above A, we want G. And above H, we want C. And then, so all this to say that if we want to calculate the volume is going to be this vector, which I'm going to, so right, this is our U, this is our V, and this is our W. So we're going to want U cross V, so we want EA. Sports, it's in the game. Sorry, I can't help it. You guys played any place in like NHL 90? Well, maybe not 90 anything, but NHL something once upon a time. Anyway, EA cross ED. And then we want to dot that with EF. And then take the absolute value of that. Okay, we're still not done. Now we actually have to do those things. So luckily we have all these vectors written down, or they're opposites. So that is the D right here. So let's write them all down. So EA cross ED. That's going to equal, so let's see, EA is the vector 9I plus, sorry, let me so you can see all the things. I know it's a mess. So EA is the 9I plus 7J plus 2K. So 9, 7, 2. And ED, well, ED is the backwards vector for DE. So it's going to be 0 minus 6J plus 5K. And then, of course, we need the I, J, K at the top of this term that we're taking. Does it matter which order you choose for the 3 vectors? Good question. Yes and no. So in this problem, it doesn't actually matter because, so not the 3 components yet. So no, it doesn't matter at all what order we choose for the 3 vectors. because yeah, in fact, we saw that last time when we did one of these calculations. I actually did it out of order and we still got the same value. So for this one, it doesn't matter, especially since we're taking the absolute value at the end. It doesn't matter which order or how we assign them. It'll always turn out to be the same positive value. What I thought you were asking, which is a slightly different question, but still the same, is does it matter which order I do these vectors in, like if it was this one first versus this one first? And the answer also in this context is no, because eventually we're going to take the absolute value. If we did do these vectors in the opposite order cross product wise, we would get the negative vector result, which doesn't matter here because we're going to take the absolute value. Yeah, this formula, no, the order doesn't really matter, which is great. So then calculating this, we're going to get, excuse me, I times the determinant of 7, 2, negative 6, 5, minus j times the determinant of 9, 2, 0, 5, and then plus k times the determinant of 9, 7, 0, negative 6. So let's see, that's going to end up being I times 35 minus negative 12, which is 47, minus j times 45 minus 0, plus k times negative 54 minus 0. So we get the vector 47i minus 45j minus 54k. And then we're going to take that vector and we are going to, sorry, back to the picture before. We're going to dot that vector with our EF. So the volume is going to equal the absolute value of this vector, 47i minus 45j minus 54k, dotted with our vector EF, which is that vector there, which is that vector there, which is 3i plus 9j minus 9k. And then you just have to monstrously calculate this thing. Why is it 0, negative 6, 5 when the vector is 6j minus 5k? Oh, so here's why. Good question. So when I drew this picture, I drew it in this way, where here's EA, here's EB, here's EF, sorry, ED. And so I was doing EA cross ED, but I had written down before on the previous page, I had calculated EA and DE. So DE is the vector 0i plus 6j minus 5k, and the opposite direction vector ED is 0i minus 6j plus 5k. So when you change the sign of a vector, you change the direction of a vector, well, they're the same thing. Changing everything to its negative changes the direction of the vector from this way to the opposite direction. Again, it doesn't actually really matter in this problem because we would still get the same value at the end because we're going to take an absolute value, but it is good to be precise, right? So if the vectors, if you have the vector, or if you have, I should say, the vector written in the opposite order, we have to change it because we would subtract in the opposite way. Good observation. Yeah, good question. So finally, calculating this monstrosity, we get the absolute value of 3 times 47 plus negative 45 times 9 plus negative 54 times negative 9, which ends up being, let's see, 3 times 47 is 120 plus 21, so 141. And then here's what I would do here. I would factor out the 9 and say I have a negative 45 plus a 54. Kind of slick, right? Not really. It's not that slick. And then we get the absolute value of 141, and that's going to be 9 times 9, which is then going to be 222. So that's the volume of this really lovely parallelepiped thing. I hope you don't have this homework problem because, as you can see, it's a lot of calculation. But if this is a homework problem you have to do, it's not so bad. It just requires, it's a lot, it's kind of a brute force problem. You don't really have much other recourse. Yeah.
So like we basically like start off with like guessing and checking.
Yeah. Yeah. So because you're given these 8 points, and so yeah, the problem is basically, right, if you do like from point to point, like there's really literally, like if you think about your picture, if you start at any corner, there's literally 1, 2, 3, 4, 5, 6, 7 different vectors you could draw. And none of them are parallel to each other, which they shouldn't be, right? If you're emanating from the same corner. So one way I tried to do this one in the past was to try and just find vectors that were, yeah, there are other ways of tackling this problem. The way I think I did it before was to say, well, I know I need 3 vectors that emanate from here. And they should kind of be vectors. Yeah, I kind of said, I know that if I look at like this vector, and I can see that that vector is maybe the sum of this vector, sorry, no, this vector and this vector, then I don't want that one because I want the 3 vectors that give me the 3 edges. Yeah. So there are other ways of analyzing this without trying to look for everything being parallel, and it might be faster. It might not be, but yeah, it's really like a guessing and checking. The units for these, we didn't specify a unit, so I would just say it's my unit cubed. If someone had said these vectors were measured in something, it would be that unit cube, but yeah, there's no units specifically here. Yeah, it was kind of a pain though trying to do it the way I did. I remember because like I was like, okay, well, I've got like all these vectors coming out of E, and then like, okay, well, I can see this one is really the sum of those 2. So that one's not the one I want because I really want the ones that aren't the sums of the other ones. So like basically, yeah, okay, fine, I'll say the things. So let me draw one more picture because you've asked a good question and I do have a good answer. So if I was doing it, and let's be super careful with my picture here. Wow, okay, he said, let's be super careful with my picture. Try and draw things actually parallel to each other. So here's the deal. If you're doing this thing, we really, really want these 3 vectors that I'm going to draw in red. We really want this one, and this one. Now, really, I mean, any 3 that come out of the corner along the edges are fine, but pick a corner and then you want those 2 vectors. And then you can see that these vectors in green, this vector coming out of here, if I call this U, this V, and this W, then this vector in green here is V plus W. This vector in green over here is U plus W. And this vector in green here is U plus V. And finally, the vector that's the whole diagonal from this corner to that corner, that vector is U plus V plus W. So if you can kind of figure out which ones are the sums of the other ones, then you can see which 3 are kind of the 3 building block vectors. I don't think it's a lot less work though, because the numbers are always kind of really kind of not nice. And so it's like, well, it looks like these 2 add up to that one, but maybe like it's a lot of playing around with it. So there's no fast way of doing it, is what I should really say. It's going to require some checking things.
Yes. Basically, we want to find the ones that are like.
We want the red ones.
Yeah.
So if you look at the vectors, like if I were to go back, well, first of all, you have to find the vectors, right? So like I would find all these vectors starting at E and then be like, okay, which 2 look like the sum of other ones, which is not the way we did it before. Okay. So hopefully you won't do that problem. But if you do, I'm happy to help if you have to do it. Like it's not so terrible. Let's move on. Let's talk about equations of lines in parametric form. So here's kind of the issue. In 3-dimensional space, we really don't have a nice equation for a line. Like y equals mx plus b. That we do in 2 dimensions. Because in 2 dimensions, you just have to be like, well, I'm going over this much and not that much. But in 3 dimensions, you have to be like, okay, I'm going this much in the x and this much in the y and this much in the z. And there really wasn't a way to say like you have kind of a slope because there's so many different directions you can go in and still have the same sort of slope thing happening. So instead, we're going to use the parametric form. And then in 21D, you'll essentially use vectors. You'll have like line equations using vectors, which are very much the same thing. So let's look at this first example. We want to write the equation of the line passing through 2 points. So we have the points P, which is 5, 1, 3, and Q, which is 6, 5, 1. Okay, so here's my line. And here are 2 points on the line. The point P, which is 5, 1, 3, and the point Q, which is 6, 5, 1. Writing the parametric equation is actually really, really not terrible. All we have to do is think about the fact that we are starting at some point and then going towards the other point. So just like with regular lines in 2 dimensions, all you really need is a point. And instead of a slope, we're going to say we need a point in a direction. Well, we have both. We have a point, we actually have 2, and we can use those 2 points to find the direction. So let's say the point is the point 5, 1, 3, and the direction is the vector from P to Q, or from Q to P, I don't care, take your pick. From P to Q, it's going to be 6 minus 5, 5 minus 1, 1 minus 3. Sorry, there's like something. All right. The other day in a different class, a bug like landed right on me. It was like very distracting. Anyway, so what we're going to do is we're going to imagine a particle traveling from left to right on this line at a constant speed, where right here at time equals 0 is when we start at P, and then 1 second or minute or whatever unit of time you want to use, we end up over here at Q. And then if you think about it, we should end up going, whoops, the same length and direction to get to the next point when T equals 2. So here's what I'm kind of thinking about. From P to Q, I go 1 in the x direction. So from Q to the next point, let's call it R, we're going to go another 1 in the x direction. From P to Q, I go from 1 to 5 in the y direction, so I'm increasing by 4. So if I increase by 4 again, I'm going to go from 5 to 9. And then in the z direction, I'm decreasing by 2. I'm going to decrease by 2 again. So I could totally find the next point by just essentially adding the vector onto that point to get to the next point. And we can keep doing that. So we can see, oh, the x coordinate gains 1 each time t increases by 1. The y coordinate gains 4. And the z coordinate loses 2. Okay, well, we can make this into an equation. The equation of our line, which again, is not a nice way of writing this, or I should say, this is the nicest way of writing it, is, well, x is going to start at 5, y is going to start at 1, z is going to start at 3, and then each second, x gains 1, y gains 4, z loses 2. So every time t increases by 1, x is going to gain 1, y is going to gain 4, z is going to lose 2. And that's how you write it. Essentially, the idea is x, y, and z are equal to the starting point plus t times the vector that gets you to the next point, or t times the vector that's in the direction of the line. So we can write this a couple different ways. You'll definitely see that in 21D, we typically write this as a vector form. Basically, we're writing the equation as a vector whose coordinate is the point at time t. This is the point on the line at t. So we can write this as r of t equal to the point 513 plus time times the vector 1, 4, -2. I feel like I should really, if I'm really saying this is a vector, I should probably say it's a vector plus a vector, even though I know it's a point. I wouldn't worry too much about this though. So yeah. So really, we can find the equation for any line. So give me any 2 points in 3 space. For example, what's the equation of the line passing through A being the point 149 and B being the point -2, 6, 20. Sorry, I keep feeling like there's something in my eye. It's really not good. In fact, you all should do this one. Find the equation of that line. There's more than one right answer, by the way. Give it a minute. Anyone gonna hold it this weekend? You guys check out hold it. It's worth checking out. Good, yeah. Sick in a good way. Not sick like it. What? Whole Earth, the Whole Earth Festival, which is this weekend. I think it actually starts tomorrow, but really gets going like on Saturday. It's a good time. I encourage you all to check it out. It's worth attending and seeing. Also, this weekend's Mother's Day, just in case you all should remember your mothers, if that's something you celebrate. So point, either one, I'd usually pick the first one. And then direction, you can go A, B, or B. It doesn't actually matter which way you do it. So I'm going to say that the direction is the vector A, B. So -2 - 1. So -3, 6 - 4, 20 - 9. So then my parametric equations are x is going to equal 1 - 3t, y is going to equal 4 + 2t, and z is going to equal 9 + 11t. Again, there's lots of ways you can do it. One way of checking that you've done it right is pick 2 values for z, specifically for t equal to 0 and t equal to 1. If I plug in t equals 0, I get the point 149. Check, it's on the line. If I plug in the point or the value t equal to 1, I get 1 - 3, -2, 4 + 2, 6, and 9 + 11, 20. you should get the 2 points that you're trying to go through if you plug in t equals 0 and t equals 1. Yeah. Sure, that's a good point. Yes. So we should say that t, you can either say is an element of the real numbers, or t is an element of the set from negative infinity to infinity, or t is between negative infinity and infinity. All of those are valid ways of saying it. Yeah, that's a good point, because otherwise you're like t could be only positive and then you're only getting an array instead of the entire line. But it also is worth mentioning, if someone was asking you to describe just a ray, which I know it's been a lot, but it might be, in case you have forgotten, array is where you start at one point and just go in one direction. So if you want the ray, then you'd be like, oh, well, t is just greater than 0. So yeah. Sure. Yeah. It's because maybe, so if t is like bounded by some inequality with real numbers, not just infinity, you might be just seeing some line segment instead of the entire line. It should, yeah. Usually I'm always thinking about just what the entire line is. So which is why I didn't write t before, because I was like, oh, well, t can be anything. But you're right, we should specify, because it's good to be clear about what our intentions are. No, yeah, it's a good question. Let's look at some things we can do with this. So where does the following line given by the parametric equations, x equals 1 plus 2t, y equal to -1, and z equal to t, where does this line intersect the plane given by 2x plus y minus z equal to 5? So, whoops, sorry, I can't see that. So we've got some line. And well, so I should point out, it's possible that the answer is nowhere. Maybe the line is parallel to the plane. So someone could ask a question, if they were not being very nice, someone could ask a question and be like, where does this line intersect the plane? The answer would be nowhere. If they were to give you that kind of question, I would hope they would say, find where this line intersects the plane, or if it does not intersect the plane, say that. I think this one intersects, but just something to be aware of. So the way we're going to find this out is, well, it has to be true that if the line is intersecting the plane, that the plane equation is satisfied. So what we're going to do is we're just going to plug in the parametric equations for x, y, and z into our plane equation. So plugging those in, I'm going to get, let's see, let's just put them all together over here. So we're going to get 2 times our x plus 1 times our y plus, sorry, -1 times our z, which is t, equal to 5. And if we solve for t, let's see, I've got 2 plus 4t minus t, sorry, minus 1. Well, I'll just do the minus t from there and then the minus 1 over here. Sorry, I got those out of order, but it's still the same. That should equal 5. So then I have 3t plus 1 equal to 5. So 3t equals 4. So t equals 4/3. Now I should point out, this is not the answer to the question. This shows that there is an answer, but the question says, where does the line intersect the plane? Well, we have to find the point. So we need to take that t value and plug it back into our parametric equations to find the x, y, z coordinate. So the point is x, y, z equal to, let's see, x is going to be 1 plus 2 times 4/3. Y is -1 and z is 4/3. So that's going to be, let's see, 1 plus 8/3 is 11/3. -1, 4/5. So that's the point on the line that intersects the plane. Kind of neat. Usually not too terrible to have to solve. Like finding where a line and a plane intersect is usually just fine. On the other hand, The next thing we're going to do is a little bit harder. So this pen is not my favorite. So in 3D space, lines can do three different things. So in 2 dimensions, you only have 2 choices. Lines can either intersect or not. They can intersect or be parallel. But in 3 dimensions, lines can cross each other. Lines can be parallel, but lines can also be non-intersecting but not parallel. They can be skew, where like one's going like, well, in fact, I've got pens, right? Your lines can be doing like this one's sitting in this plane up here, this one's sitting in this plane down here, and they're definitely not parallel to each other, but they're not intersecting either. They're skewed. They're going in different directions in planes that never intersect. Their planes would definitely be parallel. Yes, that is totally true. So, right, if the planes intersect, that's a good question. If the planes intersect, the lines have to intersect. They could still, well, I mean, so I should say, to answer your question, if 2 lines are askew, you can find planes they are in that are parallel. But the problem is a line is in many different planes, right? So I could definitely find planes that these lines are in that intersect each other, but there are also planes that they're in that don't intersect each other. So that's probably not the best way of thinking about it, but you're not wrong with your observation. So lines can either intersect, be parallel, or be skew. I suppose there is actually one fourth thing, which is technically they could also be the same. So like you could have 2 different lines that look like different equations, but are actually all the same points. Kind of like in 2 dimensions, how your lines can be intersecting at one point or be parallel or actually be the same line. But that usually doesn't happen. And if it does, it's not a big deal. So maybe we can have something like this where they intersect. 2, or we can have lines that are parallel. They never touch and the distance between them never changes, or they could even be skew. And skew is a little harder to draw. So skew, like we have this line here and this like plane, and then this line up here, and this much, much higher plane. So like this one's like above this one like that. Those don't, oops, you might like to see the things. Right, so this line is like way higher than that line there. Totally skewed. So the question then becomes, how do we tell if 2 lines written parametrically, L1 given by x1 equal to 3 plus 2t, y1 equal to -1 plus 4t, and z1 equal to 2 minus t, 2 minus t, James, it's a t, not a 2. And then the second line given by x2 equal to 1 plus 4s, y2 equal to 1 plus 2s, and z2 equal to -3 plus 4s. Do these lines intersect? Are they parallel or are they skew? So it's really, really, oh yeah. The first one, z1 equal to 2 minus t. I know I kind of flubbed the t there and started drawing a 2 instead. But that is a t. It is important when you're writing the equation to 2 different lines, if you're trying to see if they intersect or not, that you use different parameters, meaning I use t's for the first one and s's for the second one. Otherwise, it's easy to confuse yourself and think you found a place where they're intersecting, where they're not. So first thing to notice is they're very easily seen to be not parallel. And the way we can see that is their direction vector part is not the same. The L1 has a direction. Well, it's just the coefficients of t. So the direction for L1 would be the vector 2, 4, -1, just looking at the coefficients of t. Whereas L2 has a direction that is 4, 2, 4. Those are not multiples of each other, so we know they're not parallel. they're not going in the same direction. If they were multiples of each other, we'd be done. They'd be parallel, we say they're parallel. Okay, so now we have to see if they intersect. And yeah, so typically you do this piece by piece. So first we're going to set, so basically we're going to set the x coordinates to each other. We're going to get some condition on t and s. We're going to use that condition on t and s to then set the y coordinates equal to each other. And then we're going to get some other thing that has to be true. And then we're going to see if that's true for the z coordinates. And I think I can fit this in here. Okay, so we're going to set x1 equal to x2. So I'm going to set 3 plus 2t equal to 1 plus 4s. And so then I'm going to say, all right, it doesn't really matter. I guess I'll subtract 1 and say 2 equals 4s minus 2t. So 1 equals 2s minus t. And then I guess I could say t equals, yeah, this is sure. I'm going to say t equals 2s plus 1. And then I'm going to plug that in to the y coordinate one. So I'm going to say, okay, y1 equals y2. Then I have -1 plus 4t equal to 1 plus 2s. So actually, let's just solve this first. So I'm going to have, let's see. Oh, yeah. So, sorry, I'm going to back up a little bit just with the word I said. So I don't want to plug this in here, actually. I want to, oh, 1 second. I'm going to, so here's what I have so far. I have 2 equations and 2 unknowns, which should always have a solution unless they're parallel, which they're not parallel. So I don't want to plug this in over here. I actually want to get my coordinate where these intersect potentially by using these 2 equations. Question. Sorry, yeah, you're right. Yeah, good call. Thank you. Which is hard to turn the plus sign to a minus sign. The 2s minus 1. Okay. So then over here, if I do a similar thing, I'm going to get, let's see, I don't know. I think I'm going to get very similar equations. Let's see. Sorry, I'm just kind of bringing this around. 2 equal to 4t minus 2s divided both sides by 2. I have 2t minus s equal to 1. So then I'm going to try and put these together to get one point where these potential, or I should say values of s and t where these might intersect. So I'm going to, so you could set these equal to each other, or you could say t is 2s minus 1, and then you could plug this in for t here. Say, okay, well, 2 times 2s minus 1 minus s equals 1. So 4s minus 2 minus s equals 1. So I'm going to get 3s equal to 3. So s equals 1. If s equals 1, t is equal to 2 minus 1. So t is also equal to 1. Okay, so then here's what we have so far. For these to potentially intersect, we have to have the s and t are both equal to 1. There is no other way that x1 will equal x2 and y1 will equal y2. But now we have to check, does it actually work for z1 equal to z2? So z1 is 2 minus t. z2 is -3 plus 4s. If I plug in t equal to 1 and s equal to 1, it works. I get 2 minus 1 equal to -3 plus 4. So this is a point where they intersect. I should say, we have found that they do intersect. So they intersect when t equals 1 and s equals 1. So the point of intersection where t equals 1 and s equals 1 is going to be the coordinate. Well, if t is 1, I'm going to get x is 5. If S is 1, then X is 5. I'm going to check both of them, even though I know they're the same. If T is 1, Y should be -1 plus 4, which is 3, or 1 plus 2, which is 3. And Z is 2 minus 1, or -3 plus 4, which is 1. So 5, 3, 1 is the point where these two lines intersect each other. Kind of cool. Kind of a pain in the butt. So let's look at another example where the lines, I will tell you right off the bat, it's prepare for disappointment. The lines are not going to intersect. It's okay though. It's good to see why they don't intersect. So let's look at the same sort of thing. Okay, we got time. Yeah. So here's another line system. Our first line has the parametric equations x equal to 3 plus 2t, y1 equal to -1 plus 4t, and z1 equal to 2 minus t. Our second line is given by x2 equal to 3 plus 3s, y2 equal to 2 plus s, and z2 equal to -2 plus 2s. And just as a point here, again, we can see that they are not parallel because the first line has a direction that is 2 for -1.
Could you move the paper a bit down?
Oh, yep, of course.
Thanks.
Yeah, thanks. Sorry, I zoomed in a little bit. So the first direction of the first line is 2 for -1. And the second line has a direction of 3, 1, 2. Definitely not multiples of each other, so not parallel. So then we ask, do they intersect? So we do the same process. We set the x's equal to each other. Or let's just say we set the x coordinates and the y coordinates equal to each other. So the x coordinates, x1 equals x2. We're going to get 3 plus 2t equal to 3 plus 3s. The 3's cancel. We get 2t equal to 3s, or t equal to 3 halves s. Then we deal with the y coordinates. So we start with y1 equal to y2. Setting those equal to each other, we get -1 plus 4t equal to 2 plus s. We substitute in, and I think we should sub in just right away personally. I'm going to sub that in for t right there. So I'm going to have -1 plus 4 times 3 halves s equal to 2 plus s. So that's going to be, I'm going to add 1 over there. So 4 times 3 halves is 6s equal to 3 plus s. So 3s equals 3. So s equals 1. And then s equals 1 gives me back that t has to equal. Let me double check something here. Oh yeah, wow. Sorry, I subtracted 3 when it should have been subtracting s. That's not a 3s, that's a 5s. Also, sometimes my 5s and 3s look the same. Sorry about that. That should be a 5s, because 6s minus s is 5s. So not s equals 1, s equals 3/5. And if we plug that back in, we should get t equal to 3 halves times 3/5, which is 9/10. So great. Now we're going to take those two things we found for s and t and hope that they give us z values that are the same. They're not going to, but we're going to check. Do we get z1 equal to z2? So let's see, z1 is 2 minus t, and z2 is -2 plus 2s. So plugging in 2 minus 9/10 equal to -2 plus 2 times 3/5. Probably not. I mean, we can check. Let's see, 2 minus 9/10 is 11/10. And -2 plus, let's see, that's going to be -20. I didn't want tenths, but find tenths. Plus 6/5 becomes 12/10. Not quite. I'm going to get -8/10. I feel like I'm making some really smooth mistakes over here. No, I think I'm all right. Yeah, I think Grant made a mistake here. That's fine. So not the same. We don't intersect. So if they're not parallel and they don't intersect, what are we left with? That third thing, where they're skewed. So these lines are skew, which means they are non-parallel, non-intersecting lines. And last one. This last one's gonna be easy. Here are two lines. L1 is equal to, or is given by, I should say, the parametric equations. X1 is 5 plus 2t. Y1 is 1 minus t. Z1 is 3t. And L2 is going to be given by X2 is 19 plus 4t. Y2 is negative 7 minus 2t. And Z2 is 5 plus 6t. So, are they parallel? Well, since I didn't start by saying they're not parallel, probably, but let's check. The first line has a direction vector of 2, -1, 3. And the second line has a direction vector of 4, -2, 6. And we can see that, oh, V2 is a scalar multiple of V1, which is twice V1. If that's the case, if one vector is a multiple of each other, then the lines are parallel. Because they're going in the same direction. Usually we don't get parallel lines. No one's ever that nice. Like, yeah, sure, parallel lines. Right. Questions about anything I've said so far? You guys are asking good questions. I appreciate the questions. Also, I appreciate you catching my minus some mistakes because it's terrible when mistakes are made, but it happens. Right. So now we get to do the part that I think is actually kind of neat, which is where you find like distance between things, which I know doesn't sound particularly exciting. You're like, well, okay, distance formula, but it's kind of interesting. So let's look at some examples of this. And I think there's 3 or 4 different things we talk about, but let's first talk about the distance from a point to a line. Your professor, instructor, whatever, might feel like you should memorize these or might feel like you totally can just have them available to you. I don't know. So hopefully they will let you know what their expectation is. So say we want to find the distance from the point, let's call it S, 1, 2, 3, to the line given by the parametric equations, x equals 2 plus t, y equals 2 minus 3t, and z equals 5t. It's a good idea to just verify real quick that that point isn't on the line. I mean, it'd be fine if it was, the distance would be 0, but it's definitely not, because if that point were going to be on the line, well, the x, to get the x coordinate right, t would have to be -1. But if t were -1, well, x would be 2 minus 1, which is 1, but then y would be 2 plus 3, which is 5, which wouldn't be the same y coordinate there. No one's really going to ask you to find the distance between a point and a line where the point is on the line, but it's good to check anyway. So here's our line. And here's our point that is not on it. What we're going to do is we're going to find essentially some points that are on the line. At least one. So picking the lowest hanging fruit, I'm going to pick the point where t is equal to 0. So let t equal 0, and the point we're going to get is going to be 2, 2, 0. So there is my point 2, 2, 0 when t is equal to 0. And then we know that this line goes in the direction of the vector, well, 1, -3, 1. Oh, sorry, 1, -3, 5, apologies. Right, that is the vector in the direction of the line. Maybe it's actually pointing the other way. It's whatever. So here's what we want. We've got this vector v, and then we also want this vector from P to S. Let's call that the vector from P to S. Well, that's easy enough to find. The vector from P to S is 1 - 2, 2 - 2, 3 - 0. So now look at what we've got. Well, maybe it'll be helpful if I drop the perpendicular, because that's what we're actually trying to find. Right? We're trying to find this distance here. So I'm going to use some trig. So looking at that there, it looks like if I wanted to use trigonometry with this angle to find that distance, what trig function would make the most sense to use? Sine, cosine, or tangent? Well, here's definitely I know which one I don't want to use. I don't want cosine. Right? Cosine doesn't involve that side. But of the other two, tangent and sine both seem plausible. Of the two, though, well, without any other reason, I would pick sine because I know that there's some formula I know that has sine in it. Right? We've talked about how the dot product has a cosine and the cross product has a sine. I know we said less about the cross product having a sine, but the cross product does have a sine. Really, though, what I'm actually doing is I'm saying, well, I want to find this length, and I actually can find this length. Whereas I don't actually know what this length is here. Right? I don't know what that point is where the perpendicular has dropped onto my line. So I definitely want to think, oh, I'm going to use sine. Sine of theta is the length of I'm trying to find divided by the magnitude of the vector PS. So I can solve for distance and say distance is equal to the magnitude of PS times sine of theta. This is where we're going to do that trick that we use actually fairly frequently, where you see something that kind of looks like the formula you want, but it's not exactly the formula you want. Right, we know, or maybe we know, so I'm just going to remind everybody that if you want to find U cross V, one way of doing it that we never actually do is it's, or I should say really, the magnitude of U cross V is the absolute value of PS in magnitude times the magnitude of, sorry, I'm changing things around. I apologize. I'm looking at this thing over here. It'd be the magnitude of U times the magnitude of V times sine of the angle between them. So I see almost what I want. I need the other vector in there. So what I'm going to do is I'm going to multiply this by the magnitude of V. But you can't just multiply by the magnitude of V, I also have to divide by the magnitude of V. So I should point out, in case you're curious, yes, I'm totally using both notations for magnitude back and forth. Sometimes I use a double thing, sometimes I use a single thing. It's not on purpose. It's just kind of like that's what people do. So don't be distracted by the fact that I've used doubles here and singles here. They both mean magnitude of the vector. It's really laziness, to be honest. Writing the double things a whole bunch of times just gets to be a pain in the butt. But I imagine a lot of your book does this as well. So don't stress about it. I should just stop talking about it. It's not a big deal. Forget I said anything. So here's what we've got. This, the magnitude of PS times the magnitude of V times sine of theta, is exactly the absolute value of PS cross V. divided by the magnitude of V. And we can calculate these things. So here's PS cross V. It's going to be IJK. PS is -103. V is the vector 1, -3, 5. Running out of room. So this is going to equal I times this matrix determinant minus J times the determinant of -1, 3, 1, 5 plus K times the determinant of -1, 0, 1, -3. Something that I've noticed that you might want to notice is, well, let's just look at this one first. The determinant here is 0 minus -9, so I'm going to get 9i. The determinant here is -5 minus 3, which is -8, but it's plus 8j. And the determinant here is 3 minus 0, so 3k. So then I want the magnitude of that vector. So it's going to be that this is going to equal the magnitude of that vector. So the square root of 9 squared plus 8 squared plus 3 squared divided by the magnitude of V, which is the square root of -1 squared plus 0 squared plus 3 squared. So we're going to get the square root of, let's see, 81 plus 64 plus 9 is 90 plus 64, which is 154 over 1 plus 0 plus 9, which is square root of 10. Oh, sorry. Nope. Not quite. I picked the wrong vector for V. That's not my V vector, right? The V vector, that I actually accidentally grabbed the vector for PS. PS is -103. The vector V is this vector 1, -3, 5. So it actually should have been, sorry, so close to fitting it all in there. So how would you try and make everything fit? It should actually have been the square root of 9 squared plus 8 squared plus 3 squared. And then the denominator should have been the magnitude of V, which is this vector up here. So it's the square root of 1 squared plus -3 squared plus 5 squared. So the square root of 154 over the square root of 1 plus 9 plus 25. So what I want to say about this is, I don't know if you need to memorize this formula. I don't think you should, personally. I think it is better to draw this picture for your line, pick a point on your line, draw the point that's not on the line, and then use some trigonometry to find that distance. That is the way I would encourage you to think about this, at least at first, because memorizing the formula isn't going to do a lot for you. It's not going to help you think about how this actually works. So I would say, unless your teacher really thinks you should memorize this formula, I would recommend not. So let's look at another example and kind of see how something else is different. This will be the, yeah, we'll end with this next example. So let's say instead of a distance from a point to a line, now we want to find the distance from a point to a plane, which you might think would be the same kind of operation. And I guess it is the same kind of operation, but it definitely ends up having some different work to it. So let's say we have a point which is given by S being 2, 1, 6. And our plane has the equation 4x plus 6y plus 3z equal to 12. And so, like before, we want to find a point on our thing. So last time we found a point on the plane, sorry, on the line. Now we're going to find a point on the plane. So you could pick really, I mean, there's lots of options. You could pick 3, 0, 0. You could pick 0, 2, 0. You could pick 0, 0, 4. You could pick something else, right? There's literally an infinite number of choices. So let's pick I'm actually going to make a different choice than what I have in the notes just to see that it's going to come out the same. So let's say we want to pick the point 3, 0, 0. So point in the plane 3, 0, 0. Cool. And now let's draw a picture. So we've got our plane. And here's a point in it. The point 3, 0, 0. And we're going to draw two vectors. We're going to draw one, the normal vector. And someone should be able to tell me what direction this normal vector is in. What are the three components of this normal vector? Where did I get those numbers from? Yeah, the plane, right? So we talked a little last time about how a vector that's perpendicular to a plane, the components of it are the coefficients of x, y, and z in the plane equation. So if you have this plane equation, you automatically know the normal vector. And then we're also going to draw the vector from this point to our point that's not in the plane. And let's call it, well, let's just call it PS. It's P, that's S. So the vector PS here is 2 minus 3, 1 minus 0, 6 minus 0. And then we're going to draw this angle here, theta. And we're trying to find, well, in fact, let me draw a little bit more here. We are trying to find specifically this distance. Now, here's what I want to caution you against, because it's a mistake I used to always make when I was trying to draw this picture. I would draw the plane, I would draw the point, and then I would drop a perpendicular from the point onto the plane. That is what we did for the line. It is not what you want to do from the plane. For the plane, you always want to pick some point in the plane and draw the vector that both goes from your point to the point you actually want, and the vector from your point perpendicular out of the plane. But it's really easy to be like, oh, I want to find the distance from here to there, drop a perpendicular. It doesn't work. It always ends up, I mean, you can make it work, but it's bad. It's just not the way we want to do it. So I'm trying to find this distance here. Again, I'm thinking trig functions, cosine, sine, or tangent. It's never tangent. It's going to be cosine this time. Whoops. Cosine of that angle is equal to the length I'm looking for divided by the magnitude of this vector. So once again, I'm going to solve for D and get that D is equal to the magnitude of PS times cosine of theta. And then I'm looking to make one of my formulas happen. I'm either looking to make the cross product formula show up or the dot product formula show up. In this case, since it's cosine, it's the dot product formula. So I really want to add in a magnitude of this vector divided by the magnitude of that vector. So I'm going to rewrite this as the magnitude of n divided by the magnitude of n times the magnitude of PS times cosine theta. And now this top part is exactly n dotted with PS. This trick gets employed a lot. So here we're going to have n dot PS divided by the magnitude of n. And we can totally calculate that. So let's see. So let's make sure we get things right. Let's write them over here. So here's n, which is 4, 6, 3. Here's PS, which is -116. And their dot product is 4 times -1 plus 6 times 1 plus 3 times 6. The magnitude of n is the square root of 4 squared plus 6 squared plus 3 squared. So we end up getting -4 plus 6 is 2. 2 plus 18 is 20. Divided by the square root of 52 plus 9 is 61. I should point out that I didn't write it down here, but I should have. Technically, we should have an absolute value around this quantity so that in case it does come out negative, because a dot product can certainly be negative. If we're measuring a distance, it should always come out positive. So we should put absolute values around this just to make sure it comes out right.